Okay, so I did record class, but the sound wasn't recording. So I'm gonna make a new recording here so you can hear me talking as well. I think that's gonna be important. So we'll go through the quiz. I'll answer all the questions on the quiz just like I did in class. The first question about the scenario was, what are the units of each axis? And so we have two different graphs here, and this graph over here is our rate of change graph, and this is our total amount of concrete poured. So this has units of meters cubed per second, the y-axis on the left graph, and the y-axis on the right graph, or the x-axis on the left graph has units of seconds, and so does the x-axis of the right graph. And since this is our quantity graph, it has units of meters cubed. Okay, and what are the variables and functions associated with the red graph? So the function, the red graph, this is our rate of change function. So we can simply label it R sub f, because that's what this red graph is showing. And the variables are, the independent variable would be time since the pour began. So x equals time since the start of the pour. And the y variable would be, so R sub f of x is, values of the dependent variable is the rate of change of the pour. X seconds since the start of the pour. So our function is R sub f. The independent variable is the time since the start of the pour. The dependent variable is the rate of change of the pour. Then it asks for, the next question is expressing the coordinates of A and B exactly. Well, A is a point on the rate of change graph, so its coordinates are 5.2. If we want to represent that, the value of that dependent variable exactly, we're going to use R sub f of 5.2. And then B, now B is our starting point of, of concrete, and so B is also going to have be at 5.2 seconds, and that Y value of B will be the amount poured, so that would be the total amount poured to that point, F of 5.2. Really have to be good using function notation to represent values of the dependent quantity of a function. There's good application of that. Okay, so to describe their meanings, well, the meaning of this point is the correspondence of 5.2 seconds and the rate of change at that moment. And the meaning of B, point B, would be 5.2 seconds and its corresponding total amount poured at 5.2 seconds. Okay, so this blue segment here, so let me go ahead and pause the video so the blue segment is showing. So the blue segment represents, for this moment of something like 1.2 seconds here, we're showing, so that entire x-axis is showing like a moment of, say, 1.2 seconds. So it's our constant rate. At the moment x equals 5.2 seconds. Okay, it's just that this is a really big moment. Okay, so the 1.2 seconds would be a large moment. Okay, but for this moment, for our purposes in this example, we'll call it a moment, and so then we consider the rate of change to be constant at this value, R sub f of 5.2. So to write then that equation would be y equals r, it's constant, right? It's constant at this particular value of the function, and then that would be from 5.2 to 6 seconds. So writing that constant rate of change mathematically would be y equaling that constant rate, starting at 5.2, ending at 6. Okay, and then the next thing they asked for is what's represented by the horizontal and vertical segments. So here's our horizontal segment, and then here's the vertical segment. What's represented by those two, that horizontal and vertical segment? Well, that horizontal segment is representing the variable dx, or the little change in time that varies starting at 0 and ending at 0.8. Okay, so that dx varies from 0 to 0.8, and then dy varies accordingly. And how does dy vary? It varies according to the constant rate of change that we're using over here. Okay, so that dy then is equal to m dx. So it varies as dx varies according to the constant rate of change m, which is this value right here, r sub f of 5.2. So this dx is a little change in time. And again, that's a variable quantity. And then our dy would be our little change in amount poured, total amount poured, corresponding to whatever dx is. Okay, express the coordinates of point C exactly. So let's go ahead and pause here. So now we're considering the case when dx is 0.8. So now dx is 0.8, and we want to write the coordinates of C. So the x-coordinate of point C is 6. And the y-coordinate of C then would be what we get when we start from the pour of 5.2 and add this amount of concrete. So we poured 5.2, F of 5.2 meters cubed, and we're going to pour this many more meters cubed. So it would be F of 5.2 plus dy. And what is dy? dy is calculated by m dx, m the constant rate of change times the change in x. That constant rate of change is r, the constant rate of change at the moment that we used, r sub f of 5.2. So it's going to be r sub f of 5.2. That's m dx. And what's dx? dx is the current change in little change in time, which is 0.8. Almost got it to fit. So this is m dx. M is the rate at the moment, 5.2 seconds, and 0.8 is our little change in. Do that again, dx. Okay, and so 0.8 is our little change in time. So this is our m dx, and the final value of a quantity is the initial value plus how much it changed. How much it changed is calculated by constant rate of change. The rate times the change in time. Okay, so that is our coordinates of C. Okay, then it says what y coordinate is C estimating? Well, this isn't the actual amount because it's based on this constant rate of change, which is actually an approximating. So when we use this rate of change in a moment, especially a big moment, it's an approximate rate of change. So the actual amount of concrete poured would come from the actual rate of change function. So we'd expect that amount of concrete poured to be actually less than this. Okay, and so then the actual amount would be, so I'll put it right here. Suppose this is the true correspondence of 6, and F of 6 would give the true amount of concrete poured. This is using the constant rate of change to approximate the true amount of concrete at 6 seconds. So this is an estimate of F of 6, which is we know is going to be less because that rate of change is lower throughout that interval from 5.2 to 6. Okay, now the purple segment. So we want to write this purple segment. Well, the purple segment represents every correspondence point of time after 5.2 seconds and the corresponding amount of concrete according to our constant rate of change. So everything that's being shown here in this purple segment here is according to the constant rate. So every point, every correspondence point on here is going to be a time and a corresponding total amount poured. And we're going to, so that will have this form right here. So instead of having a dx of 0.8, now we just let dx be variable. Okay, so it will be y equals starting value of concrete poured plus m dx. Our m is that constant rate, r sub f of 5.2. But now, instead of being times 0.8, it's times whatever dx is. So that allows it to be for every point on this segment. Now, how can we express dx in terms of the current time x? Well, it's just final value of time minus initial. So the final time here is x, and the initial time is 5.2. So I could rewrite this dx right here as x minus 5.2. And so that would represent all correspondence points, x comma y, on this segment, which is how much, the y value is how much concrete has been poured according to this constant rate of change. At the moment, 5.2 seconds, starting from 5.2 seconds. Okay, so then we talked about, so that was the quiz. And then we talked about the second part of this homework question said to look at intervals of 0.2 instead of the whole 0.8 seconds. Let's break it up into intervals of 0.2 seconds. Okay, so instead of using dx of 0.8, we use dx of 0.2. And so then when we do that, here's how we end up approximating the rate function with intervals of 0.2 rather than an interval of 0.8. Okay, and so then what happens when we do that? Then we have to do what we did before 4 times, each one time each for the segment, the interval of 0.2 seconds. So we get an approximate for the total amount poured at 5.4, and then from there, using that amount, we calculate, using the new rate, we calculate the approximate amount of concrete at 5.6, and then using the next rate, we calculate the approximate amount of concrete at 5.8, and then finally the last estimate takes us to the estimate at 6. So this is not one single segment, but 4 different segments. Each segment showing a lower rate of change, a lower constant rate than the one before. So this is actually bending down because each of these rates is lower than the one, a little bit less than the one before, according to our constant rates over here. So then this will actually give us a more accurate estimate of f of 6. It'll be lower and closer to what f of 6 actually is. So if I put both of them up together, you see the original segment, and let's zoom in on that. So we actually see what's happening here. So this was our original using the dx. It's from dx being 0.8. And this is from 4 intervals dx is 0.2. And with the more intervals, we get these constant rates now are doing a better job reproducing the actual rate function, so that will be a better estimate of f of 6 than that will be. F of 6 being the true amount of concrete poured at 6 seconds. So, but f of 6 will still be a little bit less than that because we're still have our rates are still above the actual rate function or greater. So f of 6, somewhere, who knows, here. I'm just guessing. That'd be the actual f of 6, or the actual amount of concrete poured at 6 seconds. This is our estimate from the intervals of size 0.2, and this is the estimate from our one whole interval with this constant right here. The interval of dx is 0.8.